Hello everyone, today we're going to work through this problem of fluid mechanics, so let's go ahead and read through the problem first. Hard disk drives consist of one or more spinning circular platters that are coated with a magnetic film for storing data. A head which is attached to an actuator arm is used to read and write the data to and from the platter. The head must be positioned very precisely for the hard drive to operate effectively, and thus having a model for predicting the forces acting on the head are essential. Create a simple model for estimating the shear force acting on the head. For modern hard drives, the platter has a diameter of 3.5 inches and spins at 7,200 rotations per minute. The separation distance between the platter and the head, known as the flying height, is 5 nanometers. Assume the head is rectangular with dimensions 0.3 millimeters by 1.5 millimeters and is parallel to the platter surface. You can assume the air in the hard drive is at 45 degrees Celsius, which is in a safe operating range. Estimate the maximum shear force acting on the head. Note, the model you create based on your current knowledge of fluid mechanics will be greatly simplified and thus not very accurate. In the real system, the head won't be exactly parallel to the platter surface. A small incline with respect to the platter increases the air pressure under the head, which pushes the head away from the platter surface, avoiding what is known as head crash. In addition, the flying height of 5 nanometer is so small that the molecular nature of the air is important. That is, the air can no longer be modeled as a continuum. These two factors increase the complexity of the model beyond what's covered in an introductory fluids mechanics course. So, with a problem like this, it is important to start with some assumptions. So, what are the assumptions in this problem that will allow us to apply a model? So, one assumption is that the fluid in this example is Newtonian because it is air. Um, and what is a Newtonian fluid, you might ask? Let me go research that for you guys. A Newtonian fluid has a constant viscosity, where its shear stress is directly proportional to the rate of shear strain. This means that when you apply a force to a Newtonian fluid, its resistance to flow, or viscosity, doesn't change regardless of how fast you apply that force. Common examples of Newtonian fluids include water, air, gasoline, and alcohol. And key characteristics include constant viscosity, linear relationship, predictable flow, and the formula is the relationship for a Newtonian fluid is expressed by Newton's law of viscosity, which is tau, the shear stress, is equal to that times that. Tau is the shear stress, eta is the dynamic viscosity, a constant for a Newtonian fluid, and y dot, gamma dot, is the shear rate or the velocity gradient. And this is often represented as du over dt, I believe. Let's go back to our problem. So for a fluid, shear stresses arise due to viscous flow. This is why solids are deemed elastic, while fluids are called viscous. Basically, solids resist forces because the atoms are pushing back on the force. And fluids are called viscous because the friction between the atoms resists the flow. So any fluid that experiences a shear stress will flow. Um, So a Newtonian fluid definition is are fluids in which shear stress is directly proportional to the rate of deformation. And we now have to pick a model for our problem over here. We can model the platter as an infinite plate since its size compared to the head is very large. And the head will be the second plate that the infinite plate moves over. Um, So as you guys see over here, the main equation describing a Newtonian fluid's constitutive relationship is tau equals mu times du over dy, where tau is the shear stress, mu is the dynamic viscosity, a constant, and du dy is the rate of shear strain. For a fluid in motion, this equation extends to a more complex form involving pressure and the full strain rate tensor, leading to the Navier-Stokes equation for the conservation of momentum. which are coupled nonlinear partial differential equations describing the velocity and pressure fields in the fluid. Yes, and as you see over here, it's a Newtonian fluid because the shear stress tau is directly proportional to the rate of shear strain, or du dy. So let's go back to our problem now. So another key assumption we can make is that since the head dimensions are so small, we can reasonably assume that the speed of the platter does not vary over the head area. And we can thus assume a couette flow in the gap between the head and platter. And so, um, let's draw a diagram of that. But first, let's define what a couette flow is or means. So a couette flow describes the laminar shear-induced flow of a viscous fluid between two parallel plates or concentric cylinders, where at least one surface is moving tangentially relative to the other. Unlike Poisson flow, which is driven by a pressure gradient, couette flow is driven by the viscous drag of the moving surface, resulting in a linear velocity profile between parallel plates. This phenomenon is used in viscometry and helps model natural processes and applications like journal bearings. So some characteristics of couette flow is that the cause is the relative motion between two surfaces, such as plates or cylinders. The driving force is the viscous drag of the moving surface, not a pressure gradient. The velocity profile is that for plain couette flow with parallel plates, the velocity profile is linear, increasing from zero at the stationary plate to a maximum at the moving plate. So Taylor couette flow for concentric cylinders is where the velocity profile is a function of the radial distance between the cylinders, depending on the relative angular velocities. The flow nature is typically laminar and steady. Applications is in viscometry and geophysics. Let's go back to a problem now. So with this new information, we can draw a free body diagram of our model. So they told us that we can model the platter as a diameter of 3.5 inches, and it spins at a rate of 7,200 rotations per minute. And the separation distance between the platter and the head is 5 nanometers. So if we're looking at the plate from this perspective, so let's say that this is the plate. Then the separation between the head, which is this one, and the a plate, this gap is going to be 5 nanometers. Assume the head is rectangular. So this head is rectangular, so it will look something like this. And it has dimensions 0.3 millimeters by 1.5 millimeters. And it's parallel to the plateau surface. So we can assume that the hard drive is 45 degrees Celsius, which is in safe operating range. So yes, basically, let's look at this portion more closely. So this portion we have the rotating disc. We also have the head. Let's just draw the gap a little bigger so that you guys can actually see the velocity distribution. It's at a height h. And we assume a couette flow, which means that the velocity will be the greatest at let me see. Yes. Yeah, I think the platter is the one rotating. So let's review what couette flow. So it's linear, increasing from zero at the stationary plate to a maximum at the moving plate. So which one is the stationary plate? That is the question we have to ask ourselves. So we see that the platter is the one that is spinning So it's actually the one that will have the highest velocity. So we see that from couette flow, it has the highest velocity at the spinning circular plate. And the velocity is 0 at the head because the head is not spinning at all. So we want to find the shear force acting on the head. So the shear force acting on the head will be characterized by F shear is equal to tau times A. And this makes sense because tau is shear stress, and stress times area is going to be force because force over area is the unit for stress. So as you see here, tau, which is the shear stress for a Newtonian fluid in this case, is going to be represented by the dynamic viscosity mu times du over dy. And du over dy is wait, what is it called again? D over dy is the rate of shear strain. Yeah, so in Newtonian fluid, the shear stress is directly proportional to the rate of shear strain. That is why tau is equal to mu times du over dy. And we evaluated at so since we want to estimate the maximum shear force acting on the head, we're going to use the place where we experience the maximum shear stress according to the couette flow, which is going to be at the place where the platter is spinning, and that is at a height of y equals 0. So we define our coordinate axes as this x over here and y over here. And then it's at y equals 0, which is this portion when the maximum shear stress is going to exist. We know mu is the dynamic viscosity, but we don't know what d over dy is. So let's see what that really means. So in the Newtonian fluid equation, du over dy represents the velocity gradient or shear rate, which is the rate of change of fluid viscosity velocity u with respect to the distance perpendicular to the flow y. This term quantifies how fast the fluid velocity changes across different layers of the fluid. The Newton's law of viscosity states that the shear stress tau in a Newtonian fluid is directly proportional to this velocity gradient, with dynamic viscosity mu as a constant of proportionality. So u is the velocity or the speed of the fluid flow at a particular point. Y is the distance, which is the spatial position measured perpendicular to the direction of flow, such as from a pipe wall or a surface. Du is a small change in the fluid velocity. Dy is a small corresponding change in the distance. In the context of the equation, velocity gradient du over dy describes how much the velocity changes over a small change in distance. Shear rate. This term is also known as a shear rate because it represents the rate at which the fluid undergoes angular deformation. Viscosity. The dynamic viscosity is a fluid's intrinsic resistance to this flow and deformation. So, yes, y is what we're going to be concerned with, and y is the distance, which is the spatial position measured perpendicular to the direction of flow, such as from a pipe wall or the surface. So basically over here, that perpendicular distance is going to be quantified by this h, or this vertical portion. Basically, in order to find the maximum shear stress, we have to find the maximum velocity gradient in this case. And the maximum velocity gradient will be the location where the velocity gradient is greatest. So in most scenarios, this is where there is a steepest change in velocity or the highest velocity gradients. So it's usually at the walls or boundaries of the flow. Um, Yes, d over dy represents the velocity gradient or rate of shear strain. The maximum shear stress occurs at the walls or boundaries of the fluid flow, which is where the perpendicular from the center is at its maximum. So we can apply that to our problem. Over here, we have like two boundaries. We have one boundary, since this is a couette flow, at which the velocity is maximum, and at the other boundary, sorry, the velocity is 0. So it's actually at a minimum. So that will result in the greatest velocity gradient or greatest du over dy. So basically, the height we want to take, or the value for the change in y or the dy that we want to take, is h. And basically, this location over here is going to be h, and this location down here is going to be 0. So the dy, or in other words, the change in y, is going to be equal to h minus 0. So that will be the greatest velocity gradient. Mm, yeah. So, and yes, it's maximum at y equals 0 again because that's where the maximum velocity is, which constitute to our greatest du. So again, this tau is equal to mu times the maximum velocity there, which is equal to the rotational speed multiplied by r, the radius. And we put this over h. Um, and now let's ask ourselves, why is it omega times r? Well, it's because the linear velocity is equal to omega times r. And that's what we're concerned with over here. Let's now write down all our given information in order to more easily plug in values later on. So, uh, basically, uh, we have dp, which is the diameter of the platter, which is 3.5 inches. We have rp, or we'll just call it r, which is the radius of the platter, which is 3.5 inches over 2, which is equal to okay, I'm trying to get everything in terms of meters. So 3.5 inches over 2, and then multiplied by conversion factor 2.54 centimeters per 1 inch, multiplied by 1 meter over 100 centimeters. And this is equal to 0.04445 meters. So omega is going to be the rotational speed. So it's equal to 7,200 rotations per minute. And this is equal to 7,200 um times 2 pi radians, over 1 rotation, and then times 1 minute over 60 seconds. So this will give us 753.98 radians per second. And h is the flying height, which is going to be 5 times 10 to the negative 9 meters Because as we see over here, the flying height is equal to 5 nanometers. That is equal to 5 times 10 to the negative 9 meters. Yeah, and then we have A, H, or just A, because A is the one we will have to use over here. So A is the area of the head, which is equal to 0.3 millimeters times 1.5 millimeters. And this is equal to 4.5 times 10 to the negative 7 meters squared. And we, of course, have mu, which is the dynamic viscosity. Of air at 45 degrees Celsius. And that is a quantity that we can find easily online. Let me go Google it. So a quick search online gives us that the dynamic viscosity of air at 45 degrees Celsius is about 1.941 times 10 to the negative 5 pascals seconds. And now we have all the needed information to plug into our equation. And basically A is the area of the head, because what they're asking us is the maximum shear force acting on the head. So you have to be careful of this. You don't use the area of the platter, you use the area of the head. So rewriting what the equation for shear force is, we have that shear force is equal to mu times the rotational velocity times r over h times the area. And this is the area of the head again. Plugging in known values, we have 1.941 times 10 to the negative 5 pascals per second. And then times rotational velocity, which is 753.98 radians per second, times 0.044. Oh, wait. Yeah, so 4445 meters. Okay, over h. So h is going to be 5 times 10 to the negative 9 meters. Then the area is going to be 4.5 times 10 to the negative 7 meters squared. And calculating this all out, we have that it is equal to, let me plug that into my calculator and get back to you guys. So I got that the maximum shear force is equal to 5.85 yes, times 10 to the negative 2 newtons. So that would be the maximum force of the shear stress on the head. I hope this video was helpful to you guys. Let me zoom out so that you guys can get a clear view of everything that we went through in this problem. Yes, I hope this video was helpful to you guys, and don't hesitate to ask me questions in the comments, and I'll post this slide in the discussion, so be sure to check it out. And make sure you understand everything that was done in this problem. Thank you guys so much for watching. See you next time.